everyone, thank you so much for clicking onto the video. Today we're going to be learning about orders, rate equations and rate constants. So here are the learning objectives. The first is to explain and use the terms rate of reaction, order, overall order, rate constant, half-life and rate determining step. And then we're going to deduce orders from experimental data and from rate equations from orders of the form rate equals K, A, M, B, N. And then we're going to calculate the rate constant and related quantities from a rate equation, including determination of units. We're firstly going to recap the definitions for rate of reaction and activation energy. So the rate of reaction is the change in concentration of a reactant or product per unit time. So basically, it's a measure of how fast the reaction takes place. And the definition of activation energy is the minimum amount of energy required for a successful collision. And this varies for different reactions. So by experiment, the rate of a chemical reaction is related to the concentration of reactants by the rate equation of the form rate equals K times by the concentration of A multiplied by M multiplied by the concentration of B to the power of N. So this rate equation is for a chemical equation of the form X amount of A plus Y amount of B goes to form the products. And so what we have is actually that the rate is proportional, directly proportional to the concentration of A to the power of N, where N is equal to 0, 1 or 2. And this power we call the order of reaction. And depending on this order, all the graphs, the relationship between the rate and this concentration will be different. And so because for this XA plus YB forms products, that's why this rate equation is like this, because if we have the rate is directly proportional to A to the power of, let's say, M, and we also have that rate is directly proportional to B, the concentration of B, multiplied by N, then that means we have that the rate is equal to K times this concentration of A to the power of M, and K becomes a rate constant. And we have the same thing for B. So combining these two, we form this rate equation of rate equals K to the power K multiplied by the concentration of A to the power of M multiplied by the concentration of B to the power of N. And M and N the orders of reaction are determined experimentally, so they can't be theoretically given a value. So for the order of reactions, how we word it is that we say the order of reaction with respect to A is M, and the order of reaction with respect to B is N. And K, which is the rate constant, varies with temperature. So we'll actually come to find that K increases when the temperature increases. And the units of K depend on the order of the reaction. The overall order of reaction we would work out by adding up all the orders of reactions. So we have that the overall order of reaction would be equal to M plus N. So the definition of order of reaction is the power to which the concentration of the reactant is raised in the rate equation. So if we have rate equals K times the concentration of A to the power of, let's say, 2, that means that the order of reaction in respect to A is 2. And this is because this is the power to which the concentration of A is raised. And then the rate constant, which is K, is a coefficient of proportionality relating the rate of a chemical reaction at a given temperature to the concentrations of the reactant. So these are the other definitions that you need to know for this topic. So first we have half-life, which is the amount of time taken for half of the reactant to be used up. So for example, if we were using A, it would be the amount of time taken for half of the concentration of A to disappear. So from 2 moles per decimeters cubed to 1 mole per decimeter cubed. And the rate determining step is the slowest step in the mechanism of a reaction. So a reaction can be either one step or made up of lots of different steps. And the rate determining step is the slowest step, which determines the rate of reaction. We can actually find the order with respect to different reactants from initial rates data. And so as a recap, the definition of order of reaction is the power to which the concentration of the reactants is raised to in the rate equation. So the order with respect to each reagent can be found by doing a series of experiments where the initial concentration of each reagent is changed to see how it affects the initial rate. So if we imagine this reaction between T and U, so we've got T plus U goes to form products. So these are the experimental values that we found. And so how we work out the different orders is like this. So first I'm going to look at changing the concentration of T. So I'm going to select experiments 4 and 5 because it makes my life easier because the concentration of U stays the same. So we know that the difference in the initial rates for experiments 4 to 5 are only due to the different concentration of T. And so I like to draw an arrow. And what's happening here is that we're dividing the 1 by 2. So what's changed from experiment 4 to experiment 5 is that in experiment 5, we're using half the concentration of T. And what happens to the rate when we halve the concentration of T is that it also halves. And so this tells us that the order with respect to the concentration of T is 1 because when we halve the concentration of T, the initial rate halves. And we have the relationship of rate is directly proportional to the concentration of T to the power of n, where n is the order. So the order with respect to T is 1. And then now we have a look at changing the concentration of U. And so, as you can see, going from different experiments, there's no 2 experiments where we just change the concentration of U and don't change the concentration of T. So what we need to do is we need to use the information we've already got about T and use that along with working out the order with respect to U. So if I choose experiments 4 and 6, for T, what happens is that we multiply the concentration used in experiment 4 by 2. And then for U, we also multiply by 2. And then for the initial rate, we have multiplied by 8. So now we have a look at the concentration of T. So we worked out that the order with respect to T is 1. So if we multiply the concentration of T by 2, that means that the initial rate will also multiply by 2. And so that leaves us with times 4. And so what that means is that if we times the initial concentration of U by 2, then the initial rate we have found out multiplies by 4. And so this means that the order with respect to U is 2 because 2 squared is equal to 4 because it's not, the order isn't 1 because we're multiplying the concentration of U by 2. The initial rate isn't doubling as well, it's multiplying by 4. So that means that the order with respect to U is 4. And so now we can form a rate equation. And the rate equation would be rate equals K times T to the power of 1, and then U to the power of 2. And this will be our rate equation. And from this, we can also work out what the rate constant is, because we can do rate constant is the rate over the concentration of T multiplied by the concentration of U squared if we pick any one of these experiments, because the rate constant should always be the same as it's a constant. So how do we find the units of the rate constant? Well, here is the general method. So first you rearrange the rate equation to get K as a subject, and then you write out the units of the rates and the concentrations, and then you cancel stuff out. So it's very similar to what we did for Kp and Kc. So for example, if we had rate equals K times J squared and then the concentration of H squared, what we would do first is we would write out, we would rearrange to get K as a subject. So we would have K equals rate over the concentration of J squared multiplied by the concentration of H squared, and then write out the units. So rate is measured in, rate is concentration per unit time, which has changed. So therefore the rate units are moles per decimeters cubed per second. And then on the bottom we have 4 concentrations. A concentration to the power of 4. So we would have moles per decimeters cubed, but that would be to the power of 4. So now you can start cancelling stuff out. I can cancel this moles per decimeters cubed out. I can cancel one of these to make 3. So what we end up with is we have per second on the top, and then we have mole to the power of 3 decimeters to the minus 9. And so our units for this rate constant comes out to be moles to the power of minus 3, decimeters to the power of 9, and seconds to the power of minus 1. So now we're going to look at some questions. For the first question, deduce the rate equation and find the rate constant for this reaction from the following initial rates data. And so again, what we do first is we try and spot where one of them changes and the other one doesn't change, to make it slightly easier. So we can see that from experiment 4 to 5, the concentration of E doesn't change. They use 0.1 moles per decimeters cubed for both of them. And so I'm going to pick experiment 4 and 5. So the concentration of D changes by a multiple of 4. And then the initial rate we see also changes by a multiple of 4. So that means that we've worked out that the order with respect to the concentration of D is 1, because if we multiply the concentration of D by 4, the initial rate also multiplies by 4. And so we have that the order with respect to D is equal to 1. And now we look at E. So there's no 2 experiments where the concentration of D is the same. So again, we're going to just have to pick something that looks kind of a bit easier. So I'm going to go with experiments 5 and 6. So D multiplies by 2, and the concentration of E also multiplies by 2, and the initial rate multiplies by 4. And so because of the concentration of D, and we multiplied that by 2, that means the initial rate of 20 in experiment 5, should multiply by 2. So it should become 40. But it's multiplied by 2 as well. Doubling the concentration of E has also doubled the initial rate from 40. So we have that the order with respect to E is equal to 1. So now we can form our rate equation. So our rate equation would be rate equals the rate constant times by the concentration of D to the power of 1 multiplied by the concentration of E to the power of 1. And so that's our rate equation. To find the rate constant, we then use one of these experiments and plug it into the formula with K as a subject. So we have K equals rate over the concentration of D multiplied by the concentration of E. So then K equals, so for example, I'm going to choose experiment 4. We would have 5 over 0.1 times by 0.1. So that would give me 500. And now we have to work out the units. So the rate is measured in moles per decimeters cubed per second. And then these both are measured in and both the concentrations are measured in moles per decimeters cubed per second.